Okay, great. Well, thanks everyone for coming to the, I guess, lunch in quotes talk today. And we are very fortunate to have Nico Garavito presenting to us. Nico did his undergraduate and master's degrees in physics in Bogota, Colombia. And then after that, he joined Steward Observatory in Arizona as a PhD candidate, where he is currently working with Gertina Besla and in his final year. Nico is an expert in the dynamics and especially in the interaction of the Milky Way and LMC. And not to spoil his talk, but I personally think this is some of the most interesting implications for this interaction that I have seen. In addition to that, Nico also co-organizes Steward's Diversity Journal Club, and he has written for Astrovitos, which is the Spanish version of Astrobytes. So Nico, take it away.
Hi, Alex. Thank you so much for the introduction, and hi, everyone. Good afternoon. It's a real pleasure to give this talk. I have never visited Carnegie before, but I hope in the future I can visit and meet all of you in person. Yeah, so today I want to share what I have been doing in my PhD thesis with Gertina, which is near-field cosmology with the Large Magellanic Cloud. I'm going to show mainly what we have done so far and a little bit what we are doing, but there are more things coming out, so stay tuned. Yeah, so to start with, let's define a little bit what is the aim of near-field cosmology with the Milky Way. So the idea is to study the details of how galaxies assemble and even test dark matter models by looking at the details of our galaxy. So this is a very beautiful image that Gaia provides us, an all-sky survey, and so we can have many observations of all of the stars in the galaxy. And in particular, we are entering this era of measuring the multidimensional Milky Way. This means that we're going to have photometry, spectroscopy, and proper motions. So many kind of data. And we are going to start to reveal the outer parts of the halo, the stellar halo. So in this image, I'm showing you, so this is what SDSS observed in the halo of the Milky Way. This is what is predicted to be observed by LSST, or the Very Robin Observatory, in the next years. And in addition, we have all of these amazing other surveys and many more that this is, my screen is not big enough to put all of the surveys that we're going to have. So for sure, this opens up an opportunity to explore, this field of near-field cosmology. How can we learn about how galaxies assemble? So in particular, I want to focus on two things. That we can learn is how the Milky Way has been assembled, and then how can we compare this with what we know about cosmology, and what is the nature of dark matter. So when we talk about how the Milky Way assembled, the way we do this is now that we have proper motions and velocities, we have the 6D phase space information of many stellar tracers, for example, satellite galaxies, globular clusters, stellar streams, and then we can know what are the orbits of these objects, so where they came from, and so how the galaxy has been assembled over time. We also have results of star formation histories of dwarf galaxies, and these also tell us about that. And also we can learn about air processes, carbon-enhanced stars, tracer of POP3 stars. So this is really important. Regarding what is the nature of dark matter, what we can do in the Milky Way is, for example, measure what is the mass profile of the Milky Way, right? Which is mostly, the outer part is mainly dark matter. And also what is the shape of that halo that surrounds us. We also have the so-called small scale problem. So what is the abundance of satellite galaxies? How is that related with the amount of substructure that is predicted in the models? Also, the plane of satellites that I'm not going to talk about that, but that's something that we are looking at the present time. What is the effect of the LMC on this? Also, you can study dwarf galaxies because these are the more dark matter dominated objects in the universe, and they are inside the Milky Way if we look at the satellite galaxies. So we can learn about the details of what is the dark matter distribution in those galaxies. You can also learn about what is the halo mass function. So how many halos we expect, in this case subhalos, we expect to be in the Milky Way. And in particular, we can go to lower mass scale. So we can now test what is the population of subhalos that, for example, populate another subhalo, like a massive subhalo, like the LMC. And also we can test whether the dark matter subhalo population at a smaller scale, like with gaps in stellar streams and all these kind of things. So this is pretty exciting. However, I'm going to talk about the LMC and why we should care about the LMC when we are trying to understand how the galaxy assemble and the nature of dark matter. So to start with, let's review a little bit. So the basics of the LMC is being recently discovered that the LMC is more massive than we thought. So if you compare, this is the classical picture that we know of the LMC. Now with deeper surveys, we have seen like all the stars that are here that belong to the LMC. So it's a pretty big structure. Like if we, I mean, the distance of here is almost like 12 kpc in radius. And also the SMC is pretty big. So if we count what is the stellar mass of the LMC, is something about 2 × 10⁹ solar masses. And if we want to know what is the total dark matter content, we can use these abundance matching relationships that basically tell us, informed by simulations, given the amount of mass that is in stars and in baryonic matter, what is the amount of mass corresponding in dark matter. So these models predict that, for example, I think that like for something of the stellar mass around the LMC that we measure, what is the halo mass? And the answer is something about 10 to the 11 solar masses for the dark matter halo at the present time. There are more evidence of this that I'm going to talk about, but this is what we think now that this is the mass of the LMC. Such a massive LMC, now it was measured with HST, that the velocity is way faster than what it was thought before with new proper motions. What that was like almost 10 years ago. And now if we want to know what is the orbit of the LMC, right? How it came. So we know the present day position and velocity of the LMC. We can integrate orbits in different Milky Way models. So this is what Ekta Patel did in a paper earlier this year. And then basically for different LMC mass models, because we also have uncertainty on the LMC mass models, basically the conclusion is that even like if the LMC make a pericenter before, the pericenter is around 4 or 5 gigayears. But the evidence point that basically the LMC is coming for the first time. Right? It's the closest approach is just happening for the first time at 50 kpc. Before, if there were a previous pericenter, it was about 100, 120 kpc. Okay, so summarizing what we know about the LMC right now, it's coming for the first time into the Milky Way. It's inside the stellar and dark matter halo of the Milky Way at 50 kpc, right? And its mass is about 10% to 25% of the mass of the Milky Way at infold. So before the LMC entered, that's what we thought that is the mass of the LMC. Such a massive LMC should have some consequences and some perturbations that we should observe, right? Because it's inside the stellar halo, right? And it's very massive. So there should be consequences about this ongoing interaction. And the first one is, if you have a massive LMC, a big LMC, it should bring its own satellite population. And thanks to Gaia, now we have proper motions of many of the satellite galaxies in the Milky Way. And then we can integrate orbits and see where they came from. And so this movie, and this work from Ekta Patel, we include also the effect of the SMC. And what I'm showing here is, you see how the SMC and the LMC are coming from the right. And they're bringing all these satellite galaxies that are orbiting around them, right? So this is evidence that the LMC is bringing around 3 to 6 satellite galaxies. So these are satellites of satellites for the Milky Way, right? I'm gonna play it again. But doing this work, we also realize that it's not only that the LMC is bringing satellites, but the LMC is perturbing the orbits of the satellites of the Milky Way. So this is another effect that we care, right? That we need to include the potential from the LMC when we do this orbit calculation. Okay, but there is more evidence. This is not only the only evidence. The other evidence comes from stellar streams, which you can see here. So these are these paths of stars, which are color coded by distance. So these are coherent structures. And basically they form because if a globular cluster of satellite galaxies orbit around the Milky Way, you see that by the tidal interaction with the Milky Way, it's gonna develop these tails, these leading and trailing tails, right? So these are these stellar streams that are very nice and they observe. The nice thing about the stellar streams is that with the tails, you can tell about what is the orbit, and because there are so many of them, and in different regions of the sky, you can measure many properties of the Milky Way. But one interesting result that came like 2 years now by Sergei Kopusov and Denis Ferkal and their team is that if you use Gaia, the proper motion of Gaia, you can measure now what are the velocities of these stars in the stellar stream. So in particular, in the Orphan stream, which is this stream here, they measure the velocities of the stars, and this is what is shown on the right. So the velocities are these now illustrated with these arrows. And as you can see, in this southern hemisphere, because they also discovered that the streams goes to the southern hemisphere, it's almost perpendicular to the path of the stream, and this is not expected. I mean, in the movie that I showed before, the velocities should be aligned with the orbit of the stream, right? So this is why is this happening. So the explanation for it is that there has to be a perturbation that is causing this, and this is in the galactic south where the LMC is, and the best explanation is that this part of the stream is feeling the gravitational interaction with the LMC. And the best LMC mass model that explains this, or like the amplitude of these shifts in the velocity, is an LMC with a Darman halo of 10 to the 11. So again, consistent with what's predicted before. But then this not only happened to the Orphan stream, this was something that is systematic in many streams in the southern hemisphere. So this is beautiful work by Nora Sheep and collaborators, and basically showing, again, the purple arrow here is the velocity of the stream. And then you see that there is a systematic misalignment in these velocities with the track of the stream, which is shown in black. Again, when you include the LMC, you find that something around 10 to the 11th solar masses can explain this. And I think that's work in prep that is coming soon, modeling these streams with the LMC. But this is consistent. And more recently, there was a paper by Vasiliev and collaborators which tried to fit the so famous Sagittarius stream that has been really hard to do in the last decade or so. What they do is, now that we know that the LMC is important, they include the LMC and model the Sagittarius stream. So you see that the data is these squares, blue squares here. This is all the path of the stream. And then the dotted lines, the lines are the models. The model that don't include the LMC is the yellow one. And you see that it's really hard to measure to fit the properties of the stream. That's why it couldn't be done before. But now that we include LMC models, you see that they can actually reproduce the shape and the morphology of the stream. So this is very exciting and is basically highlighting the need to treat the Milky Way halo as a time-evolving potential that includes the perturbations from the LMC. Okay, so coming back to this, why this matters, because I'm talking about near-field cosmology. So it matters because now we have these exquisite proper motions, and we're going to have even better proper motions and radar velocities. And if we want to compute the orbits of satellite galaxies to see where they're coming from, we need to include the LMC. Otherwise, we're going to be biased. The abundance of satellites, I showed that the LMC is bringing its own satellites. So again, it's important to measure how many satellites the LMC bring to put constraints on the model. And this also affects halo mass functions and there might halos, subhalo population in stellar streams, because the LMC is also expected to bring its own populations of Darmadu subhalos. Okay, so now that we know that it's important, how can we model this? And now we really want to understand what's a massive LMC doing in the halo. So these are simulations that I presented last year in a paper, and I'm showing here on the right panel. And you see an LMC coming and interacting with the Milky Way. You also see a cat. I didn't simulate the cat, but hopefully the cat is illustrating that there is a motion going on in the Milky Way, right? And this is going to be important. Something that I want to remind about this, or say about these simulations, is that they reproduce the orbit and the present day position and velocity of the LMC within 2 sigma of the HST observations. So it's very precise. It's a simulation tailored to what we think that is the orbit of the LMC. Of course, there are assumptions. For example, I assume a spherical Milky Way halo at the beginning of the simulation, and the same for the LMC. The SMC is not yet here, but it's a start to understand what's going on in the halo, what other perturbations we should expect. So the first thing I think that coming from the cat that I showed is that you see that there is a motion of the Milky Way. The Milky Way is not rigid, is not fixed in a space, it's moving due to the gravitational interaction with the LMC. So what I'm showing here is on the x-axis, this is time, and 0, 0 is the present time. So this is the present position of the disk. This is the center of mass of the disk. And then when you go back in time, you start to see that where the disk was at the beginning of the simulation. And we see that in different LMC mass models, I have different LMC mass models, we get like a spatial displacement up to 50 kpc in 2 gigayears. And being on the bottom panel, you see the cumulative displacement, and we see that 50% of that motion is happening in the last half of gigayear. The displacement is not only in position, it's also in velocities. In velocities, we get something around 60 kilometers per second at the most. So the disk is moving with respect to where it was, 60 kilometers per second. And again, 50% of that motion happens in the last gigayear. And this is going to be very important for later, so keep this in mind. In addition, the Milky Way is not a rigid body, so we don't expect that the whole Milky Way moves with the center, with the cusp, where the disk is. We don't expect that. So if we measure now, this is distance, and this is the center of mass of different shells in the Milky Way, in the simulations, we get that basically things like inside 40 kpc move with the inner parts of the Milky Way, including the disk, but then the outer parts are offset from that motion. So this is the displacement of the cusp due to the LMC. And the corresponding effect in the velocities, now in this case, this is the radial velocities, is that you induce a dipole between northern and southern hemisphere. The lines here show different LMC mass models, but then you get offsets in the dipole up to 100 kilometers, 120 kilometers per second between north and south, just because of this. And this is what is known as the reflex motion. Is this apparent motion of the outer parts of the halo with respect to the inner parts. And this has been studied. It was first predicted in models in Facundo Gomez, 2015. Then I run these simulations, which are now with a live embodied simulation, and then Mike Peterson and Dennis Erkat also are all finding this. And we are all finding, agreeing that the major contribution or motion of this happened after 30, 40 kpc. So consequences of this, I think that sometimes people ask, oh, the Milky Way is in equilibrium, or is not. It's not that the LMC is messing up the entire Milky Way and we are like in a major no, but it is that our reference frame is not inertial at the moment, especially because we are in this maximum of movement in the inner part that I showed in the last slide. What effects from this, for example? So Dennis Erkat in 2020, earlier this year, showed that if we want to measure the mass of the Milky Way, that we do with kinematics of halo tracers, so like globular clusters, satellite galaxies in the outer parts of the Milky Way, these mass estimators usually depend on the velocity and on the distance. And they can go far away, right? Like at 100 kpc. But now we know that there is this offset and their corresponding reflex motion in velocities. So what he did is like he applied these mass estimators that are commonly used and as a function of distance, and he got a measurement of the mass, which is shown with the symbols, that is way above of the actual mass in the simulations, right? So when you take the ratios, you can take like, depending the mass of the LMC and different models, you get that you can be off by almost 50% when you measure the mass of the Milky Way. So this is why it's important. And again, it's not that the Milky Way is in disequilibrium, but it's that our reference frame needs to be corrected if we want to do that. We want to measure the mass. Okay, but this is not the only thing that is happening. And this is what I want to focus mainly. It's that as the LMC comes, it will induce, like, I mean, the dark matter halo is going to respond to this interaction. So in this movie, what I'm going to show you, this is the density contrast. So this is the density relative to what initial was the density of the Milky Way without LMC. And this is the density. So you see that, well, sorry, let me play this again. See that here is the LMC coming with the black. And then when you see this is the density of the dark matter, you see that you start to increase the density. So red is way dense, more density. So you see that you create this strong overdensity behind. And this is what is called the dark matter wake. This is responsible for dynamical friction. So this absorb, or like, this is a way that the halo absorbs the angular momentum and energy of the satellite, in this case the LMC, and that's why satellite galaxies eventually decay into the centers of the galaxies. Otherwise, they will be there around forever, right? An interesting thing about the dark matter wake is that it's strong. It has to be the strongest dark matter wake in the Milky Way, because the LMC is the most massive satellite, and it's coming for the first time where the wake is the strongest. Detection of the wake will be proof the existence of dark matter in a different dynamical regime, because usually, you know, dark matter is being measured around galaxy halos, but they're like in equilibrium. But a measurement of this dynamical wake will provide further and new clues about dark matter, and I'm going to talk about that. So, for example, we know that, I mean, of course, our best candidate is WIMPs and cold dark matter models, but there are other models because we haven't found the dark matter particle yet. So there are models like as fluid dark matter models, or fuzzy dark matter models that are very popular right now. And in a paper earlier last year, it was shown that if you have different dark matter models, and in this case, this is different just velocities of the perturber. So the perturber is here, and this is again density of dark matter. You will get different dark matter wake shapes. This is the only difference here is the velocity of the perturber. And in this kind of dark matter model, in fuzzy dark matter model, it matters if you are supersonic or subsonic. So you will get different shocks and different dark matter wakes. And then in month, you can think that in month that this modifying Newtonian dynamics, where there is no dark matter. We also expect, in this case, it's not a dark matter wake, but it's a stellar wake, because we have a perturber, and then this is again density. So you get like these conic shapes. In this case, will be in the stellar halo, not in the dark matter halo. So in principle, if we can detect this dark matter wake, we could distinguish and put constraints on what is the nature of dark matter. So to summarize this, this is the Milky Way, and this is what is going on due to the LMC. First, you have this transient wake here. This is the classic dynamical friction from Chandrasekhar. And we have this huge now overdensity, which is due mainly to the cosp motion that we saw in the beginning. So the disk is moving like in this direction, so we get the opposite overdensities just because of that. So these are the two things. We call this the collective response. So these are the two things that are happening on the galaxy. Now, how we characterize this? Now, okay, this is fine. This is all the theory. What about in reality? How can we measure this? So for this, we need multidimensional data. And this is great because we're having that. So this is now being shown in galactocentric coordinates. This is how, on the top right, this is how the wake will look like. So you see the wake where the LMC was. This is doing a slice as a function of distance in the halo. You see the collective response here too. So it has a very particular distribution and signal in the sky. And very important is that it's large scale. These are large scale perturbations. So ideally, if you have all sky surveys like Gaia that can go up far in the halo, you should see this. Even if there are substructure in the halo, you should see this because these are large scale. So this should be on top of this of the substructure. We also expect we have particular signals in the velocities, not only in the densities. And this is work that Emily Cunningham characterized in this year, earlier this year. And we have velocities in radial velocities and in all the components of the velocity, we expect a very particular signal that we should be able to measure. And this is, for example, at 45 kpc. So you see, again, the reflex motion inducing this in radial velocities. And the wake in this case, you can see it here in radial velocities too. And then you see these flows in both the tangential components of the velocity. Okay, this is good. However, will this be observable? Like, so far in our models are very idealistic in the sense that we don't have a stellar halo that is being accreted over time as we expect. So what I did is I basically, first, I would like to know what is the precision that we need to measure this. So in this plot, this is all the substructure in the halo that is beyond 20 to 120 kpc. So the first thing you see is this long Sagittarius stream, and then you also see thin streams. But there are regions that are free from substructure, or maybe that we don't know yet, but we don't expect something big as Sagittarius. So if we look at these regions in particular, so I make like, you can take density ratios in these regions or compare the velocity kinematics, because we are expecting like a global kind of signal. If we look at particular regions, we can get knowledge about the signal that we are looking for. So I look at, for example, what are if Gaia could observe this, or LSST, at least in proper motions, and we are interested in the region which is between 50 and 80 kpc. This is where the wake will be stronger. And with Gaia, it seems that we are looking at difference between 50 kilometers per second or so. So maybe this could be done with Gaia, with giant stars only. Just looking at those regions that I showed earlier, comparing there. And with LSST, it looked like we could also do it, but it's like in the limit. However, like, I mean, the worst case is for proper motions actually, but for radial velocities, we don't need that much precision. We just need this number, a lot of stars, because we want to see these global patterns, and the signal in the radial velocities is strong. So for radial velocities, I think, yeah, we don't, even with 20 kilometers per second errors in the velocity beyond 50 kpc, we should be fine. And with densities as well, we just need precise distance. But with tangential motions, it seems that it might be harder. Okay, so, and people start looking at this. So soon after I published my paper, Vasily published this paper, which basically it was looking at our layer stars in Gaia and beyond 60 and 100 kpc. So there are non-structures, for example, the Sagittarius stream is here and also in this part. But there was something that it was kind of seen before in a smaller scale, but he saw it in a larger scale, which is this overdensity here. And this is what is called the Pisces plume. And what is interesting is that it doesn't look that it's associated with Sagittarius stream. It doesn't look like a coherent substructure, like something from a thin stream or something. And it's long, it's like from 60 to 100 kpc, and it's in the region where you expect the wake to be. So this is the first hint of that maybe this is the wake or not. We need more data. If we can map this maybe with other tracers beyond our area, that would be great, because that will provide us maybe more coverage. We can see if the substructure is also there. So this is pretty interesting, but still we need to do further investigation, right? Okay, but now we know that there is a lot of substructure, so how that might bias or affect the detection of the wake. So the first thing is, okay, there is also Sagittarius. What about the wake of Sagittarius? What does that? So we had a simulation with Sagittarius, and then in these plots, I'm showing the densities of what you expect from the wake of Sagittarius. And a good thing is that Sagittarius is in a plane perpendicular to the orbit of the LMC. So you expect the wake to be like at this longitude, like a zero longitude, basically. But when you compare to the wake from the LMC, which is here on the right, is not as strong. I mean, the wake from the LMC is way stronger. And this is the residual. So you basically, I mean, the halo is mainly perturbed by the LMC. And this is because the LMC is on first passage, where the wake is stronger. Sagittarius is less massive than the LMC and has been orbiting the Milky Way for longer, and therefore the dark matter halo has had time to relax. And so the LMC should generate the strongest dark matter wake at the present time in the halo. However, there could be like more substructure in the halo. Is not only Sagittarius, and in particular, we are worried if it could if it would be difficult to detect the kinematic signature from the wake if there are substructure. So this is what Emily did. She compared what is the kinematic signature from different halo models that have different accretion events. So you see all these accretion, and this is taken from the Bullock and Johnston simulation. So you see different kind of accretion events, like what if you have circular orbits, what if you have early accretion, you see that the kinematic signature is almost vanished because the halo have already, the substructure have time to relax. You have radial orbits, you also don't see much. You have high luminosity satellites, then you see a stronger imprints of that. You have recent accretion, of course, you also see it. So yeah, how does this compare to what we are measuring? And look that the velocities here are from -200 to 200, and in our simulations are from -40 to 40. So it seems that it would be hard, right? Like, so we compare, and what we did is we characterize this using spherical harmonics and compute the power in the spherical harmonics to see which one, I mean, to see how these two compares. So this is showing the power spectrum of all the simulations. So the one with the LMC is shown in pink, this shaded region, and you see that it's strong, but there are models from the accreted halo models that are stronger. For example, the ones that have recent accretion or the ones that have high luminosity satellites. And yeah, so different panels show the power spectrum in different velocity components. However, so we see that, yeah, these two are stronger in particular, but we don't expect this to happen in the Milky Way, because, I mean, the most recent was Sag, and was a long time ago, so it was not recent. So we don't expect to have this kind of signal. We expect something more about the other signals. And in this case, the signal is going to be comparable to what we are expecting from the Milky Way. So there is hope. However, we need to do further investigation, because here we are comparing two different simulations, and ideally we would like to have a simulation that have recent accretion events, like different accretion events, and the LMC as well, to be self-consistent. So there are more work to do, but this is already like good news. Like, you know, there is a chance there for the velocities. And when we compare the velocity with the simulation with Sag, so that's the one in purple, and the one with Sag is the dashed line, we see that, yeah, with Sag add a little bit of signal there, but mainly is modulated by the LMC as we expected. So this is good. Okay, so coming back here again, what is new now? What can we learn about dark matter with the LMC? So one new thing that I added here is characterization of the dark matter wake. That would be an additional proof of dark matter and has the power to constrain dark matter models. And now I want to talk about, for the rest of the talk, about how the LMC is changing the mass profile and the shape of the halo. And why is that important if we want to compare with the predictions from cosmology. Okay, so in general, why it's important to measure halo shapes? The idea is that in the Milky Way, for example, we use the information of the halo shape to derive quantities. For example, what is the mass of the Milky Way? We assume spherical symmetry often, or particular shapes. When we want to integrate orbits of a star, we have to assume what is the shape of the Milky Way halo. And interesting, like the cold dark matter theory predict that halo has to be triaxial. And often we want to compare our Milky Way with what is predicted. So we use like the Milky Way, like hey, we want to know if it's common or it's not. So we want to place it in a cosmological context. Using properties, for example, what is the shape? Is the shape of the Milky Way common in cold dark matter theory or not? But if the Milky Way has this perturbation from the LMC, we need to really know what is the LMC causing before we go to compare to mean galaxies that are not taking, that doesn't have an LMC like satellite, right? So this is what I'm doing. So this is the shape. Now this is the shape of the Milky Way with the LMC. So the Milky Way is here and the LMC with the dot here. And then you see all kind of like shapes here that change as a function of distance and everything. So the first thing that we can see just by eye is that the shape is not axisymmetric, it's really asymmetric. And it's being affected by three things mainly. One is the LMC, which is here, but also the dark matter debris, because the LMC, I mean, it's a live system and it's being stretched, and it should have also a debris of dark matter, which by the way should be the largest dark matter debris in the Milky Way as well. So, and that can also be detected, but that's subject for future talks. And also have the dark matter wake. So we can remove the LMC easily, and then we can focus on what is the effect on all of this, of the debris and the wake on the shape of the halo. So this is what is shown here. So now I remove the LMC, I just show where it was, but now here we don't have LMC particles. We have the debris particles, but not the LMC particles that are bound to the LMC at the present time. And still, the shape is not axisymmetric, like it's very asymmetric. And yeah, in particular, the LMC, the debris is providing like 50% of the mass of the LMC is now in this debris. I mean, don't take these numbers super seriously, but it's something around 40 to 60% around that. Like it changes with models and many assumptions, but it's a non-negligible mass that is out there. And now if we remove the debris, this is what we get. So now this is just the effect, like this is the wake and the collective response here. So you see that the wake should be here, and you see how the halo shape contains information of the wake. It's still not axisymmetric. Yeah. Yeah, this is how the LMC look like at the present time, but we are not taking into account when measuring the shape. And just to be complement, this is how the debris look like and how the wake look like, corresponding to panel B and C. Okay, so if you want to quantify the shape, we know that it's not axisymmetric, how we do that and how we compare that with cosmology. So common prescriptions for halo shapes are like prolate or oblate, which is, so for prolate is like this, like a football. And for oblate is like this, like a pancake kind of shape, or shapes in between, triaxial shapes, right? This is what is commonly used to describe halo shapes. What we're doing here is trying to characterize these shapes using an expansion in spherical harmonics again, because here we can really characterize all the asymmetries in the halo. So this is what we are doing in this case. And for the Milky Way, this is what we get. So you can, here L and M are corresponding to these spherical harmonics here. So 0, 0, this is the monopole, right? Here. So, and the color means what is the power or like the amplitude of the contribution from those terms. Interestingly, of course, the monopole is the strongest, but then we have the dipole, right? So this term here, which of course come from the collective response mainly, and also some contribution from the dark matter wave. And then we have many other terms, but basically these two, right? When we compare to what cosmology tells us, or like how we parameterize those halos, so this is coming, I took common triaxial halo shapes from Eddie Chua, that he characterized these halo shapes in Illustris, in the Illustris simulation. And this is what the outcome of those simulations, like in particular, if we have these three shapes that are common in cosmology, how they compare to what we're measuring. So one thing is that none of these halos have non-axisymmetric terms because all these prescriptions are axisymmetric. So by doing that, we are measuring important information, like we don't have the dipole here, right? So the first conclusion is axisymmetric models sometimes are not the best way to characterize this halo, right? We need to go a little bit further if we want to understand what is the shape of the Milky Way and to compare it with cosmology. Especially the dipole, like we don't get the dipole, so like, I mean, yeah, that's an issue. And here, like just by comparing this, like the Milky Way halo is not oblate, it's not plural, it's not triaxial. We cannot use these models to describe the halo shape of the Milky Way. So now that we compare, now we can sum over all the M terms, and we can now see here, like, okay, how the amplitudes at least compare. If you take the triaxial model from cosmology, how that compare with what we just get from the wake and the perturbation from the LMC. And it looks like it's pretty similar. Like, yeah, there is some difference in the quadruple term, but if you just look at these even terms, the amplitudes are pretty similar, which means that if we want to put the Milky Way in a cosmological context, ignoring the LMC, we're going to be biased, or ignoring the perturbations from the LMC, we're going to be biased, because we are going to say, yeah, this looks like triaxial, have same signal, so the LMC, the Milky Way is triaxial, and this is common in lambda CDM. But it's because we are ignoring the perturbations. So first of all, we need to characterize this, and then we can see what is the underlying triaxiality of the halo. Okay, so to conclude this part, the shape of the Milky Way has information about the LMC's interactions, have the wake and the cusp motion, the inner part motion. Methods to measure the Milky Way halo shape need to account for interaction with the LMC. So I didn't talk about how the Milky Way halo shape is being measured, but it's mainly with stellar streams. And these methods, as I show with the Sagittarius stream, that now can be fitted. So this measure that include the LMC perturbation now, I mean, this is the way to do this now, right? We need to include the LMC. Axisymmetric models do not account for the halo shape in the case of the Milky Way, and the presence of the LMC complicates efforts of placing the Milky Way in a cosmological context. And I want to stress this because it seems to me that we cannot compare the shape of the halo of the Milky Way with a standard or Milky Way like galaxies in cosmology, because we are living in a particular time which is in this interaction with the LMC. Okay, so what is the future now? By doing all these spherical harmonic things, the main idea also is because we can characterize the density and potential, and we can do this as a function of time. And the beauty of this is that we can capture the halo response of the Milky Way, so the wake and the cusp motion again, and all the distortions in the halo using this methodology. And this could be used to compute orbits. So this is what I'm showing here on the right. So you see two test particles here. One is feeling the interaction of the Milky Way and the LMC, and the other one is static. And you see immediately that the orbits differ a lot. This orbit integration was done using this methodology, like using all the decomposition in spherical harmonics, and it was done like in seconds in my laptop, and it includes all the dynamical information of what is going on in the halo. So this is also a way to do very efficient orbit integrations. So this is what I'm going to publish hopefully at the end of this year or early next year. And this is going to be publicly available for the community in this in the Python code Gala. You can see here, written by Adrian Price-Whelan. So we're implementing this in that, so everyone has access to these models and can integrate or stellar streams or everything, whatever. So yeah, we plan to release in 2020 and 2021. In particular, then what I'm gonna do is like build a stellar halo, like a more realistic stellar halo in this kind of potentials, to then study what will be the properties of the wake, of the stellar wake counterpart to the dark matter wake, and how can we help to guide observations using these simulations. A fun thing that we can also do is, with this, is revisit what are the satellites from the LMC, because now we can capture also the distortions of the LMC halo. So this is also, I presented this is just at the present time, and it's basically showing are the relative velocities of these LMC satellite galaxies with respect to the LMC. And from this, I get that from the 6 proposed satellite galaxies of the LMC, 2 of them are bound to the LMC at the present time. So it was a fun calculation to see like how the distortions in the LMC halo can affect what are the population of the satellite, population of the LMC. So with that, I want just to stress that these are exciting times because we are going to have many, many data. We have nice ideas of how to proceed further about testing dark matter and learning about the assembly history of the galaxy. And I added, here like 2 new things in particular for dark matter is and the wake, and also finding the dark matter debris. So this is something really interesting to see if we can find in the near future. So to conclude, first, modeling the dark matter halo response to a massive LMC on first infall is critical to test cold dark matter models and to record the assembly history of the galaxy. The LMC induces a dark matter wake that should be observable and a potential test bed for the nature of dark matter. The LMC induces a reflex motion that results in a strong dipole in the kinematics of halo stars that also should be observable. And the LMC induces non-axisymmetric dark matter distributions in the Milky Way dark matter halo, and therefore the Milky Way halo shouldn't be parameterized with oblate, prolate, or triaxial halos. And finally, I presented new models of the Milky Way LMC interaction that will inform future studies to account for the LMC. So thank you so much, and if you have any questions, please let me know.
Great. So you can do the emoji, or if you want to unmute briefly to clap for Nico. That's thanks so much.
Thank you.
Okay, we have time for some questions. And I think you can raise your hand and I will look for it there, or put it in the chat, or just unmute and start talking. And I can maybe kick it off. So I'm interested in, so you focused a lot on the LMC and Milky Way, which I think with good reason, but I'm wondering if you've thought about how this affects, for instance, what we should be seeing in like clusters of galaxies. At what point, they have like these very careful lensing maps and all of those things. Is this a thing that, is this, 50% seems like a lot. Is that a sort of thing that you could detect potentially in that sort of environment?
Yeah, that's a great question, actually. And I'm not an expert on lensing, and I read a little bit of how these models are done, but I think that definitely it's worth it to think of how to, if we can measure wakes in other galaxies, and in clusters of galaxies. I know that now strong lensing in particular is being used to try to find subhalos and dark matter substructure in lensing. So my naive intuition is, yes, like if there is a strong wake, we should definitely try to look for it. And I think it is really important that we do that, because we will have like extra information, like a statistical sample of dark matter wakes. And I think that will be more powerful if we want to constrain the nature of dark matter, because so far, we haven't detected yet the wake in the Milky Way. But even if we do it, then it would be one wake, right? But it would be nice to have more and have more constrained, more powerful the dark matter nature. So I think that that's a really good point. And yeah, we have thought about this, but we haven't done anything yet. But yeah.
Okay, thanks. Ting?
Yeah, so very nice talk. And so all the simulation here or study you are doing here are only considering LMC, or SMC is also considered, and or that's probably negligible.
Yeah, no, that's a good point. We start just with the LMC. We haven't included the SMC. I think, definitely we should include the SMC. It is hard because it's hard to find the present day position of the LMC when the LMC is also being perturbed by the SMC. It's really hard. It takes a lot of time, a lot of tries. But I think that, we should do that. Yeah, I don't expect that we're gonna.
Yes, the other way to ask the question, do you expect the result you predict for the from the wake will
Yeah.
be different when SM?
Yeah. Yeah, I mean, I expect to change, but a little bit, but not like drastically, like saying, oh no, the wake now is not there and it's in another location. No, the wake should be there. Maybe change the strength, a little bit the morphology, all that kind of stuff. But I think that is not going to change drastically. Neither like the reflex motion. I don't expect to be that to change by orders of magnitude. Yeah.
Great. A question from Xiaolong.
So in your talk, you mentioned the weak due to the satellites in different dark matter models. So could you explain a bit more the difference between like the fuzzy dark matter and the cold dark matter? And if we assume that dark matter is fuzzy dark matter, what is the signature we expect in the observation?
Yeah, that's a great question. And I didn't tell much, but in this particular case of fluid dark matter, you can have, so these particles are way lighter than cold dark matter particles, like WIMPs. These are, orders of magnitude lighter, and therefore they have this quantum effect, so they can interfere with each other. So we expect to be different to cold dark matter because of that behavior. So the shape of these waves should be different. But also, like for example, in cold dark matter, I mean, the shape of the wave doesn't change drastically. I mean, if you go supersonic or subsonic, like, I mean, yeah, it doesn't change. But in this case, we see like there are drastic differences, right? The hard thing is that if we want to do that, I mean, this is very sensitive to the orbit. So this has been like a DL test, like in wind tunnel kind of effects. If we want to make a specific prediction for the LMC, we need to, I mean, to do this kind of simulations with the LMC. And the same for MOND. Like we need to, there is way more work to do this, but I think that it's kind of, it's promising that we can start look at what would be the differences in the weight expected from the LMC in different dark matter models. And I should say that there's a grad student starting with Cortina that is going to look at this particular problem, how dark matter, the weight from the LMC looks in different dark matter models. But I don't have an exact answer now, like what should we expect? Like what would be the main differences? I don't know yet, but there will be differences.
But so should the LMC be in the subsonic or supersonic regime
yeah, that's a great question. So the LMC moving like I think 340 kilometers per second, so it's close to supersonic. So that's why it's in this paper it was hard to predict what will the LMC because it's right like in the limit. So yeah, we need to do the simulation. Okay,
thanks.
Great. Other questions for Nico? I have another question then about the sort of detectability in spherical harmonics that you pointed out. So it looked like those were specifically looking at the power spectrum with respect, this one. This was, I guess, the next slide after this.
Yeah.
Was looking at the power spectrum in velocity space. Does it help if you, I guess, either do it all together with all of the velocity somehow, or if you like add in the density information, because the, saying that you detect a flat, if you just look at the pink and the green lines on the left one, it's just going to be a flat signal across.
Yeah.
And that left part to the decline of the green it seems hard.
Yeah. Yeah, great question, Alex. The answer is yes, I think it would be more powerful to combine kinematic and density data. However, that is hard. From these methodologies, it's hard to do. It's not clear how to combine both the kinematic and density information. But it's something that we are thinking of. And that's why Emily did this, because we first want to know how things look in the kinematic space. And we're definitely thinking about going that direction, but it's not clear yet what will be the results. but yeah, we should definitely start thinking about this multidimensional analysis rather than by components.
Okay, cool. Thank you.
Mm.
Okay, last call for questions. Okay, well, in that case, thank you so much, Nico, for a really wonderful talk. And so claps are in order.
Thank you so much, Alex, for having me. It was a real pleasure to be here virtually, but
yeah.
Yeah.
Great. So I think you still have time on your schedule this afternoon if anyone wants to meet with you, is that right?
Mm-hmm. Yeah.
So yeah, so you can sign up on the Google Doc and Nico will check it. But otherwise, thanks and see everyone next week. Happy weekend, whatever that means now.
Thanks,
Nico.
Thank you.
Thank you.